Hello, I'm Ben McCreath, and today I'll be talking about developing your methodology for size exclusion chromatography on the Acuity APC system. So with size exclusion chromatography, it's been around for 60 years now, and it provides a crucial set of data. So you have your molecular weight moments, so your molecular weight averages of your polymer distribution, and the visual indication of the population of your polymer chains in solution. There has not been a lot of advancement in this area for over that period until the advent of the APC back in 2013. And today I'd like to talk about some of the advances in the method development that technology brings to the table. So to understand the APC, you need to understand at the core, at the heart of this system is the column technology. So with the APC, we use hybrid technology. So as opposed to traditional GPC where you have polymeric beds, these use a hybrid material which give you a lot of the benefits of the rigidity of silica, but with less of the downsides of things like the interactions that silica presents. For the method development, the most pertinent aspect of this is the swelling behavior of these particles. So polymeric beds, depending on what solvent that they are in, which mobile phase, they're going to swell to a different extent. This doesn't happen with APC particle technology, and that's one of the key parts to opening up further method development for your system. This leads into not only the higher efficiency, which is why you may want to use this system in the first place, but also the ability to optimize your solvent, your mobile phase. And for those of you that use something like light scattering, it's good to know that these are very low shedding straight out of the box. So when we're talking about method development, we also have to talk about method transfer. So the APC is going to give a higher level of resolution compared to traditional GPC, traditional size exclusion chromatography. So you're not always going to get the same answers because we're going to give you more information on your polymer distribution compared to what you may have been used to. We've also got a different column chemistry. And this again could lead to slightly subtly different results from traditional polymeric columns compared to the APC column technology. But now we have a greater ability to optimize the method. And so all these things combined means you may not have identical data, identical distributions compared to your traditional method. So you need to do a full method transfer and validation of your new methodology. If this is not possible, then you can still use your traditional 30 centimeter GPC columns on the APC system. You just won't have the advantages of the APC column technology, but you can still run these systems, both the GPC columns and the APC columns, alongside each other on the same system. So on the screen now, you can see a full method development system where you have your APC system, you have multiple column compartments that will house different sets for APC, but also another column compartment which will house traditional GPC columns. In this system, we also have solvent selection valves to enable you to use all of these different combinations as you need in your laboratory. So we're going to take a systematic approach to developing the APC methodology. So first of all, we're going to define the analysis goal. Then we're going to look at the method development factors, and finally the data processing and reporting options to us. So what is the driving analytical requirement? So if your maximum resolution is your key requirement, then first of all we must select the correct column type and porosity for the target polymer molecular weight distribution. We then optimize the column bank based upon the combination of the solvent viscosity, the desired flow rate, and the available system pressure. If speed is our goal, we want to maximize throughput. We still need to first select the correct porosities, and then we can optimize on the various column lengths available. So we have 150 ml, 75 and 30 ml column lengths are available for the APC technology. And this allows for very fast, high throughput, but still high resolution analysis applications. And then of course, what information do you require? Which basically lends itself to what detectors do you need to ensure that are in your system. Let's give a quick example of high resolution. So this is one of the primary reasons to use the APC technology. This is where we've combined multiple small pore columns in a bank, which allows extremely high resolution of this low molecular weight liquid epoxy resin. So you can see excellent resolution all within 5.5 minutes. Looking at high throughput, then here's an example of a dextran calibration curve. So just a 4-point calibration curve. We're talking high throughput, so we're going for throughput over maybe the accuracy and precision. And this is just a single short column, and you can have this calibration and this order of magnitude from at the low end, you've got a resolution of 47,000 all the way up to a couple of million. That's all done within half a minute. So extremely high throughput capabilities here. And if you're looking at information, there's various levels of information you can be interested in. So for example, there are a number of detector options for the APC. Your conventional acuity APC detectors include the refractive index detector, which is kind of your universal, your go-to detector for polymer characterization. We have photodiode array, which is more sensitive to polymers that may have a chromophore or additives with a chromophore. The tunable UV, and also evaporative light scattering detector, which is useful if you have poor or no chromophore available. But we also have available third-party detector options which have been developed since the advent of the APC, which include light scattering detection, which is excellent for a accurate molecular weight, and a viscometer, which provides the universal column calibration or structural information of your polymer. So depending on the level of information you require, you can select the detectors to suit. So here's an example of molecular weight accuracy with light scattering. So in the case here, you have an 85,000 EVC standard. If you look at a conventional calibration, then it's going to give you, against polystyrene standards, 111,000. So it's very precise, but it's not accurate. If you use light scattering detector, then it brings the accuracy to the experiment, and you get your 85,000 molecular weight as expected. Structural information, so the viscometer is the best detector for this. So that same PVC sample, if you look at the Markov plot, which is looking at the molecular weight versus the intrinsic viscosity, then you can actually see how the compactness of the polymer in solution compares. So in this case, you've got different polymer classes, so polycarbonate, PVC, and polystyrene, but also to tell you what's happening within your polymer distribution itself. So in this example, you can see some branching occurring in the PVC. You may want to take further structural elucidation studies, so take this offline. So for example, take it to an NMR or a mass spectrometer. So for this, you can collect fractions off the APC. So you collect the smaller fractions, which you can then take offline and do further studies with.